Welcome to the Explainer. So, have you ever slapped the water in a swimming pool and just watched those ripples spread out? Or maybe you've plucked the string of a traditional karar or a guitar and felt it intensely vibrate right there in your hands, filling the whole room with music. Well, today we're focusing exactly on that. We are tackling the core concepts of Grade 9 physics, specifically Unit 6. We're going to uncover the hidden physics of motion and sound and really break down exactly how energy moves through the world around us. Okay, let's dive right into our roadmap for today. We're moving from the micro to the macro. We'll start with the basics of oscillation, then build up to the anatomy of a wave, apply all of that to the actual physics of sound, and wrap up with wave interactions.
All right, Section 1. The basics of oscillation, looking specifically at pendulums and springs.
To truly understand massive waves that can literally cross oceans, or how sound can fill up a huge concert hall, we actually have to start small. We need to look at the simplest component first, which is periodic motion. Now, the definition is a to and fro movement that repeats itself over and over in a fixed time interval. I know, it sounds super technical, right? But you actually experience this constantly. The steady beating of your heart, the ticking of a grandfather clock, or even just the rhythmic push of a kid on a playground swing. Those are all perfect, everyday examples of periodic motion in action. It's really just a repetitive motion governed by time.
Now, what is truly fascinating about the math governing a simple pendulum is actually what's completely missing from the equation. The formula for a pendulum's period, which just means the time it takes to complete one full swing back and forth, is t equals 2 pi times the square root of L over g. Do you notice what isn't in there? Mass. There's no m. Whether you hang a tiny little pebble or a massive iron boulder at the end of that string, the time it takes to swing back and forth depends only on the length of the string, that's the L, and the local acceleration due to gravity, which is the g. Because of this brilliant simplicity, a perfectly measured pendulum is actually an ideal tool for calculating the exact gravity right where you happen to be standing.
Moving from the pendulum, we have another classic oscillator to talk about, the spring. This one is defined by Hooke's law. It states that the applied force equals the spring constant, K, times displacement, X. Let's break that down physically so it makes sense. Think of K as just the stiffness of the spring. A super stiff spring has a high K value, meaning you need a huge force to stretch it, right? While a loose, slinky kind of spring has a low K. So the crucial point here is that whenever you stretch or compress a spring, it instantly generates a restoring force. It desperately wants to pull or push the mass right back to its resting spot, its equilibrium. And it's exactly this endless physical tug-of-war that creates the periodic oscillation. Okay, moving right along to Section 2, the anatomy of a wave. Let's see how this all builds.
When we take those single oscillations we just talked about and chain them together, we get a wave. A wave is a disturbance that moves from its source, accompanied by the transfer of energy without the transfer of matter. Now, this is a massive concept to grasp, absolutely crucial. Waves carry energy, not actual particles, across a medium. Think about when you flick a really long rope. The rope itself doesn't fly out of your hand and shoot across the room, right? Instead, the physical energy travels through the rope, while the actual bits of the rope just kind of bob up and down in place.
Based on how those particles actually move, waves are split into two main types. On one hand, we have transverse waves. This is where the particles move perpendicular to the energy transfer. Again, think of that up and down flick of a guitar string while the wave itself shoots horizontally straight down the neck. On the other hand, we have longitudinal waves, where the particles move parallel to the energy. They pulse forward and backward. Think of a sound wave physically pushing air molecules together and then pulling them apart in the exact same direction that the sound is traveling.
To really master your Grade 9 physics, you've got to know this essential wave anatomy. The period, or T, is the time required for one full cycle. Frequency, which we measure in hertz, is how many of those cycles happen every single second. Then there's amplitude, which is the maximum displacement from equilibrium. Basically, it's just how tall the wave gets. And finally, wavelength, which is the actual physical distance between two crests. Make sure to keep these terms locked in your mind because there's a fundamental vocabulary we need to decode the rest of this explainer.
Which brings us perfectly to Section 3, the physics of sound.
So now we're going to apply these anatomical wave rules to the macro real-world phenomenon that we literally experience every single day, the sounds all around us. Remember how longitudinal waves work? Well, sound propagates exactly like that. First off, it strictly requires a medium to travel through. We're talking air, water, wood. It absolutely cannot travel in a vacuum. No medium, no sound.
It relies entirely on compressions, where vibrating objects physically slap the particles in the medium, shoving them tightly together, and rarefactions, where those particles are pulled back apart. This pulsing, invisible force intensely vibrates and compresses its way through the air until it physically strikes your eardrum. That is exactly how you hear the world.
Now, what's truly fascinating here is the massive jump in speed across different mediums. In air at 0 degrees Celsius, sound travels at 331 meters per second. But in water, it jumps all the way up to 1,493 meters per second. And in solid iron, it absolutely skyrockets to 5,950 meters per second. I mean, wow. Why does it do that? Well, because the particles in liquids and solids are packed so much tighter than they are in gases. This means the vibrational energy can transfer much faster from one closely packed particle to the next one over.
And that brings us to a classic everyday mystery. Why do you always see a lightning flash before you hear the crash of thunder? It's something we've all noticed, but solving it unlocks exactly how environmental factors completely dictate wave propagation. Let's break down the physics behind this thunderstorm mystery step by step. First, light travels incredibly fast, effectively instantly as far as our eyes are concerned, whereas sound just kind of lumbers behind. Second, the speed of sound in air actually depends heavily on temperature. Like we said earlier, it's about 331 meters per second at freezing. But third, and this is key, warmer air allows sound to travel slightly faster. The heat physically alters the medium. It causes the air molecules to bounce around more rapidly, which in turn transmits the thunder's mechanical wave faster. So the physical state of the air completely dictates the speed of the wave.
This temperature dependence actually unlocks our next concept too, sound refraction. Because sound speed depends on temperature, sound waves can actually change direction. They literally bend. During the day, the air right near the ground is warmer, making the sound travel faster at the bottom. This bends the wave upwards, away from the ground. But at night, the air near the ground is cooler, so the sound wave slows down near the ground and bends downwards. This totally explains the surprising fact of why you can often hear distant sounds, like a train horn or highway traffic, so much more clearly in the dead of night. The sound is quite literally being bent down toward your ears.
All right, let's move into our final segment. Section 4, Wave Interactions and Superposition.
We know how single waves travel now, but what happens when multiple traveling waves crash into one another? Or when they get trapped bouncing back and forth off hard surfaces? The answer lies in the superposition principle. It states that when two or more waves pass through a single point at the exact same time, their instantaneous displacement is just the sum of their individual displacements. Basically, they just add together. If two crests meet, they constructively build each other up into one massive wave. But if a crest meets a trough, they destructively cancel each other out, leaving you with flat water or just total silence.
Let's apply that principle. When two identical waves move in opposite directions, like a wave bouncing off a wall and coming right back, they superimpose to form what we call a standing wave. It consists of nodes, which are points of zero displacement where the waves perfectly cancel out, and antinodes, which are points of maximum displacement. Connect this right back to that guitar analogy from the very beginning of our explainer. When you pluck a string that is pinned down at both ends, the wave bounces back and forth, creating these exact standing waves trapped perfectly between two fixed points. And that is exactly the physics of how musical notes are created.
Which leaves us with one final, kind of provocative thought. If sound strictly requires the physical vibration of a medium to travel, what does the universe sound like in the total vacuum of space? Since there's no air, no water, no particles to violently bump into each other up there, space is completely terrifyingly silent. Even the largest, most explosive star dying in a supernova makes absolutely no sound at all. Take that away with you today. Sound isn't just an energy, it is the environment itself vibrating. Thank you so much for joining me on this explainer. I really hope this structured journey makes your grade 9 physics unit totally clear, and I'll catch you next time.